All right, so today we're going to start with something called a separable differential equation. I'm just going to read it, the universal DE. Now, a separable differential equation starts off with basically anything of the form dy dx equals f of x times g of y. If I have a function of x and a function of y that are connected as a product, and by the way, this could also be a quotient because your g of y could be 1 over something. If I have them connected as a product, it's a certain type of solution. If they're connected as a sum, it's totally unrelated. And in a Math 255 class, you look at every possible type of differential equation. In this class, we look at this one specifically. And what I would do is I would then move the g over. Then upon integrating both sides with respect to x, I would get something that looked like this. Remember, dy dx integrated with respect to x is the same as integrating with respect to y. So if the problem starts off like this, we can actually fast forward it into something that looks like this. And we'll do some examples. And we'll also look at variations of the way a problem is stated. So let's consider, we want to solve, okay, let's start off with something like this. I want to solve dy dx equals, how about the cosecant of y over x cubed? Now that first, that looks really, really scary until I realize all I've got to do is separate it, because think of this as cosecant of y times 1 over x cubed. So they are connected in a way that I can separate them. And the separation, I'll do the formal and then I'll show you that you can fast forward it just a little bit. The first thing I'm going to do is multiply both sides by the reciprocal of the cosecant, which of course is the sine function. So I'd have the sine of y dy dx equals 1 over x cubed, or if you'd like, x to the negative third for purposes of integration. Now, at this point, I can just do this. Integrate dx, integrate dx. Okay, when I do that, the left-hand side will become sine y, dy dx integrated with respect to x is dy because there are no actual x's in that statement. The right side being x to the negative third dx. So going back to the original statement, in a sense, it literally means that I can take the dx and throw it on the other side from a notation standpoint. That's not what we're actually doing, but from a notation standpoint, you can see, oh, it's like I'm taking the dx and sticking it over here and then integrating. And the only reason I can do that is because of the nature of the product, so that I can pull these apart in the way we just did. So now when I integrate this, I'm going to get negative cos y equals negative, in this case, negative 1/2 x to the negative 2 plus c. Okay, that would be the same as negative 1 over 2x squared plus c. If I multiply, oh, let's call that c1. Let's do this. If I multiply through by negative 1, then I'd have positive cos y equals positive 1 over 2x squared, and then we'll call it plus c2. That's just the negative of c1. Now, at this point, we are completely done with the calculus. The only question that remains is, how should we represent our final answer? Well, since the question was dy dx, clearly y is a function of x. X is my independent variable, y is the dependent variable. So it means I should, if I can, solve for y. So at this point, I can solve for y, and I'd have an inverse cosine. That's one possible way of representing the answer. I'll put it up here. So y equals the inverse cosine of this quantity here, 1 over 2x squared plus c2. This is an absolutely correct, acceptable answer. But another version of this answer would simply be to put these two on the same side and write it as cos y minus 1 over 2x squared equals c2. This would be equally acceptable because there's just less work in arriving at that. And if it were possible, it would even be acceptable to solve for the x. So generally, the rule of thumb is if you can isolate the y, do so. And if you can't, don't worry about it. Just put x and y on the same side. That's still considered an acceptable answer. And here's the reason this is so important to understand. You're solving a problem and you're going to use this answer later on in some other bigger problem. So the way you express your final answer, it's not about right and wrong. It's about what would be the most useful form. And usually isolating the y is going to be more useful because I'm going to have to substitute it in for other in other equations perhaps, or maybe I'm going to have to take a derivative somewhere along the line, something like that. So the final form of the answer, both of these would be perfectly valid forms. Now, this is one form of the separable differential equation. The other form that is common, and I want you to understand that it's a form, it's what you'll often see in a textbook or in an actual problem that you have to solve, a situation. It might be a physics class, for example, this will come up. And that is if you have something in the form, I'll use the same f of x dx plus g of y dy equals 0. This is an alternate form of the exact same differential equation, or the same type of differential equation. Dx and dy are not quantities, they are instructions, but I cannot integrate this exactly yet. What I want to do is put them on opposite sides and then integrate. So the rule of thumb is if the problem is expressed in this form where the dx and the dy were separated, it's equivalent to if I threw it over and rewrote it as dy dx equals something involving f and g. But this is probably the most common form that you'll see the problem stated as. So let's do a really simple one. Let's do y squared dx minus e to the x dy equals 0. And then I'm going to tell you that y of 0 equals -1. Now, that last thing is what's called an initial condition. We did one of these the other day with population growth. The initial condition means my final answer will not have an arbitrary constant. We will be able to figure out the value of the c. So you say, oh, I'll just integrate both sides, except we have a small problem here. I've got y at dx, x dy. Mathematically, it's an absolute impossibility that I could integrate either one of those. The variables aren't matching. And x and y cannot both be independent variables. So I need to do a little rearranging. Well, the first thing I'll do, I'll throw this guy on the other side. Okay, now I can move things around nicely. So what I want to do is multiply both sides by the reciprocal of the terms that are there. So I want to multiply both sides by e to the -x and by y to the -2. Then algebraically, I know that statement is true. Now, dx and dy are not quantities, they are instructions, and they are now instructions that I perfectly can handle. So I am going to simply integrate. Okay, so the way I went about this, I got the dx and dy on opposite sides, and then I made sure the function of x went with the dx, the function of y with the dy. That's actually quite critical. Again, dx and dy, I don't ever say dx equals or dy equals because they are instructions. They are the instructions of the integration. Without that dx there, I wouldn't know what I'm supposed to do. So now let's go ahead and integrate, and I will get -e to the -x. Here I'll get negative y to the -1 plus c. Okay. If you don't like that, you can always write this as -1 over e to the x equals -1 over y plus c. It might be a little easier to interpret now. Now, you can find the arbitrary constant at any point in the problem. I would prefer to find it sooner than later. I don't want to manipulate this and carry the c around. Let's just go ahead and find it right now. So this means when x is 0, y is -1. So when x is 0, y is -1. So let's look and see what that would be. If x is 0, I'd have -1 over e to the 0, which is -1, equals -1 over -1 plus c. So I've got -1 equals 1 plus c. That would give me c equals -2. All right. So at this point in the game, I've got -1 over e to the x equals -1 over y minus 2. Now, solving for y would not be difficult at all. But if you wanted to just simply leave it in this form, if you wanted to rearrange it, if you wanted to put the y on the other side, all roads are correct. Now, one of the things I notice here is that I got all negatives here. There's nothing wrong with that, but maybe I want them to be all positive. So I could multiply both sides. What I would probably do in this case, because getting y by itself would not be that difficult, I would probably do this. Throw this on this side, throw that on the other side. Then I'd have +1 over y equals +1 over e to the x minus 2. I would like to take the reciprocal of both sides, then I can say y equals. But in order to do so, I need this to be one quotient. So if I do this, this would be 1 minus 2 e to the x over e to the x. I have 1 over y equals this quantity. So the final answer, my bestest, mostest answer I can give would be y equals e to the x over 1 minus 2 e to the 2x. That's probably the cleanest form, not the only form, but the cleanest form of an answer in this case. So this is the nature of a separable differential equation. It's a differential equation I can solve by simply integrating both sides, one with respect to x, one with respect to y. Now, I'm going to show you one of the first applications of this, one that we can do in this course. Now, we've already done it with the population growth, Newton's method. Those were very, very specific types of separables. If you go back and look at them, they fall into this category. But I want to do something slightly different. We're going to do something called an orthogonal trajectory. Now, there's a word there that a lot of you are not familiar with, the word orthogonal. So I want to go over what that word means. It's a mathematical word that I use every single day in my Calc 3 class. If in a differential equations class, in a linear algebra class, we use the term all the time. Now, a lot of people liken it to perpendicular, and that's not a bad comparison, because if something's perpendicular, then it's orthogonal. Orthogonal isn't necessarily perpendicular. Now, what does perpendicular mean? Perpendicular is when things meet at right angles. So perpendicular is between lines, planes, lines and planes. So if you look at your walls in your house right now, all of your walls should be perpendicular to each other. If I'm standing with good posture, I should be perpendicular to the floor. Perpendicular is any time you can measure a right angle between things, but the things themselves have to be straight. You can't measure an angle between curves. That has no meaning. So what if I have a curve and I had another curve that intersected like this, but then when you check the tangent lines to these two curves, you found that the tangent lines met at a right angle. Although curves cannot be perpendicular, we would say these two curves are orthogonal. And similarly, in 3 dimensions, if I took a basketball, okay, if I took a basketball and then I took a stiff piece of cardboard, when I place it on the basketball, it will touch the basketball at exactly one point, and that would make it what's called a tangent plane. Okay, now think of the center of the basketball and then going out through that point, like the little spout where you fill in the air. If I went from the center and I went right out the basketball, what I'd have is a line that is perpendicular to the plane, but orthogonal to the surface of the basketball. It's crazy. So orthogonal can happen with curves, and there is something perpendicular in there. That's kind of the idea. So orthogonal trajectories are when I'm trying to find a whole bunch of curves that are orthogonal to a whole bunch of other curves. And let's start with something really simple. Let's start with concentric circles. That means circles that share the same center, okay? So if I considered concentric circles centered at the origin, then the equation of those circles would be quite simply x squared plus y squared equals r squared, where r is the radius. Okay, so the radius could be 1, 2, 3, 7, 25, but the radius would be a non-negative value. So I have an infinite number of circles, all centered at the origin, all having a different radius. What I would like is, what is the set of all of the curves that exist that are orthogonal to every single circle at the same time? Now that's crazy. So you might say, well, maybe it's parabolas, maybe it's a logarithmic function. There is something out there where if I drew it, it's going to be orthogonal to every single curve simultaneously. Well, how am I supposed to figure that out? Well, how do we measure perpendicular lines in remedial algebra? We say that lines, when the product of their slopes is -1, then we say the lines are perpendicular. So if I had a line, let's say y equals 3/2 x plus 5, and then I had another line, y equals -2/3 x plus 1, we'd say these lines are perpendicular because the products of the slopes is -1. Another way of thinking about it, if one of the slopes is m, then the other one must be -1/m. Sometimes we refer to that as the negative reciprocal. So I would take the reciprocal and change the sign. That's the easiest way to create perpendicular lines. Well, I don't want perpendicular lines, but what I want are all of the curves where the tangent lines to all of my curves are orthogonal to all of these tangent lines. Okay, so at this point here, I'd have a tangent line that looks like that. I'd have a tangent line. I'd have a tangent line. So I want a set of curves. So the first thing we'll do is find dy dx for this curve. And to do that, we have to differentiate implicitly. So if I take the derivative with respect to x of both sides, just to remind us, if I do d dx of x squared plus y squared, okay, that's a function of x. So when I differentiate this, I'll get 2x plus 2y dy dx, that's the chain rule factor, equals the derivative of this, but r is a constant, so that would be 0. Okay, that means that 2y dy dx is equal to -2x. So dy dx, if I throw that over, is just -x over y. So another way of saying that is at every point on the circle, the slope of the tangent line is nothing more than -x over y. Now that's the tangent line at every point on the circle. I want the set of all the curves where the tangent lines are orthogonal to these. So what I want to use all the curves where dy dx is, flip that over and change the sign, positive y over x. Okay, again, just like with lines, I want to find the reciprocal and change the sign. So I want every curve that exists where dy dx is y over x. Okay, is that going to be easy to find? Well, that's a separable differential equation. So I know exactly how to find it. Since that is a separable differential equation, I'm going to go ahead and erase this. I don't need this anymore. We want to solve this separable differential equation and see what family of curves this produces. Well, like before, I'm going to multiply both sides by 1 over y and then integrate with respect to x. Or you can just be lazy and say, I want to move the y over and I want to move the dx over. So I'm going to get 1 over y dy equals 1 over x dx when all is said and done. Okay, again, 1 over y dy dx, and then I integrate both sides with respect to x. I'm going to get this. Now, if you stare at that for a moment, say, wait a minute, I'm going to get a couple of natural logs there. This will give me the natural log of the absolute value of y equals the natural log of the absolute value of x plus, let's call it c1. Solving for y here looks like it could be really messy. So what we're going to do is we're going to move this guy over. And then we have log of absolute value of y minus log of absolute value of x equals c1. And now using a log property, we know the difference of the logs is the log of the quotient. So on the left side, I have the natural log of the absolute value of y over x equals C1. Now I can exponentiate both sides. Aha. Now C1 can be any real number, positive or negative, because we know that the log, right, goes from negative infinity to positive infinity. If I do e to both sides, I'll get this. And let's just call that, how about C2? Because if C1 is any real number, then e to the C1 is any positive real number. Now notice it would have to be positive, but then again, we did have the absolute value on this side. So now if I multiply both sides by the absolute value of x, I'm going to have the absolute value of y equals C2 times the absolute value of x. Wait a minute. That'd be like saying y is plus or minus C2x. Aren't these just lines passing through the origin? Stare at that for a minute. Oh my gosh. Every line coming out of the origin is going to be orthogonal to every one of these circles simultaneously. Now that's kind of cool. Now I chose an example that produced a really friendly set of orthogonal trajectories, but this is an example of how you would use it. So orthogonal trajectories are, we find dy dx for the original function, then flip it over, change the sign, and we solve that separable differential equation to find this family of curves that are orthogonal to all my original curves. So it's a kind of a cool application, okay? Before we move on to the next thing, hold on a second. Are there any questions? Oops, let me go back to, go to gallery view for a second. Does anybody have any questions on this?
Yes. Okay. Yes, I want to ask that, does the trajectory need to be like a particular to just one tangent line?
No, it has to be, this line has to be orthogonal to every one of these circles, which would be the same as saying it's orthogonal to every one of the tangent lines to every one of the circles at the same time. So I'm going to have infinitely many circles. This one line alone is orthogonal to every one of them. That's what's crazy. How do I know that? Well, that's what we did. We created the situation where that would be true. Okay, it's kind of cool because you go, wow, I can always do this. Well, to a point. You could have something that's too complicated to integrate too. So be aware, this is only going to work if you keep it so that it's a separable differential equation. And there are problems that are really gnarly and you won't be able to do that. So, you know, unfortunately, it won't always. All right, let me go back to here. Okay, now we're going to move on to the next thing, which is our first of our integration techniques. All right, I'm going to have to use a paper towel soon. The more I write, the harder it is to erase because the ink kind of builds up. Okay. Now consider the following. If I said differentiate u of x times v of x, I have two functions of x and I want you to differentiate them. Well, clearly that's going to involve product rule. We know this from Calc 1. So we would have the first, and if you want to just write it as u, it's implied that u and v are functions of x, times the derivative of the second, plus the second times the derivative of the first. Make sure that looks like a v. All right. Well, that's pretty exciting. The derivative of u times v is u dv dx plus v du dx. Yeah, I know that. But now think about integrating both sides. So if I now said, let's find the antiderivative of both sides. Now on the left side, I'd have uv. On the right side, I'd have the antiderivative of u dv dx integrated with respect to x plus v du dx, again, integrated with respect to x. Okay, I'm not doing anything here. This is Calc 1, except, wait a minute, dv dx integrated with respect to x. Isn't that the same as what we've been practicing? Isn't that u dv? And then this here would be plus v du. This gives us a really cool little formula here. So why would this be a cool little formula? Just suppose for a moment that I asked you to integrate something that was in this form, and you did not know the antiderivative of this, but you did know the antiderivative of this. Then you could say that the integral of u dv is equal to uv minus the integral of v du. I'm just rearranging this. Remember, we started with product rule, but this formula here basically is an alternate way to do something where I don't know that answer, but I do know that answer. Now, there's no guarantee. I'm saying if that's the case, I can change the problem around in such a way that I can easily do this. This is called integration by parts. Okay, we're going to do a whole bunch of examples. Give me one moment. I'm going to grab a wet paper towel now. All right. Now, this is going to be the first of many integration techniques that we are going to learn and then hopefully master over the next few weeks. Okay, so integration by parts, part of it is, how do you even know that's what it is you're supposed to do? Well, actually, it's pretty simple. I have an integral of a product of two things. I have an integral of a product of two things. So let's suppose that I'm asked to do something like this. I want to do the integral. Oops, hold on, I need a drawing paper towel now. We're still a little bit too wet. Okay, let's suppose I have the integral. I'll keep it really simple. I've got the integral of, let's say, x e to the x dx. Now, you don't know any function whose derivative looks like that. You know how to differentiate x e to the x. But can you think of a function that when I take its derivative has exactly one term written as a product? You're saying, I can't do that. So what we have to do is decide which one of these is the u and which one of these is the dv. And by the way, if I can integrate both of those terms, then generally either one of them can be u and either one of them can be dv. If one of the terms I cannot integrate, then it has to be the u because I can't go backwards. So let's suppose that we decided that we're going to let u equal e to the x, and then we'd write our dv as x dx. Then our du, just like in formal substitution, we'd say is e to the x dx, and v would be, now you're going to integrate, but you don't actually have to write the integral, just write the antiderivative. My v would be 1/2 x squared. We don't write the plus constant yet. We wait until the complete end of the problem and then we write the plus constant, because it may be the case that we have to do more than one integration along the way. And at the end, we're going to have a plus c. All right, so everything I said is true. Okay, everything I said is valid. And so the next thing we write will be uv. So this is equal to u times v. So 1/2 x squared e to the x minus the integral of v du. So minus this integral. So minus the integral of 1/2 x squared e to the x dx. Okay, it is an absolute that this quantity here is equal to this quantity here. We couldn't integrate this because we have a product of two things, one of them being an x. Notice that we now have a new integral with the product of two things, and now we have an x squared. That feels like this got worse. It feels like this got harder. Now, remember, I said we could have picked either one of these to be the u and either one of these to be a dv. So I want to point out, I like to use a lot of movie references to show the calculus. You know, those who were in my Calc 1, right? We used the garbage pit of the first Star Wars movie when the walls are closing in. That's how we actually proved the fundamental theorem of calculus, you know, delta x going to 0, all that kind of stuff. Well, in the third Indiana Jones movie, right? That's the one where they had the knight and he had been up there for like 1,000 years or something, and he had the Holy Grail. And you remember the bad guy had to choose. Now, I'm not giving a spoiler alert. This came out like 1,000,000 years ago. And he has to choose. And he chooses badly. And like all good Indiana Jones movies, he shrivels up and does all this stuff. And a lot of people don't realize it wasn't that he chose badly of the Grail. Right behind the knight, there's a big whiteboard with some calculus going on. And they were doing an integration by parts problem, but they were doing it for life or death. And you had to choose the appropriate variable in your integration by parts, or you would shrivel up and die. And he chose poorly. If you remember, that's what the knight said. You see, everything I wrote is true. But this integral isn't easier, it's harder. That doesn't mean I can't do this problem. That simply means I needed to change my choice. It won't always work, but what happens is with a very little bit of practice, you get the hang of it and you see what you need to do to make it work. So although that integral is true, I won't be able to evaluate it. So instead, we're going to let u equal the x term, and then dv being e to the x dx. Then my du is simply 1 dx, and my v is still e to the x. Now you'll notice my new problem, uv minus the integral of v du. So that's just minus e to the x dx. And that integral is simple. The antiderivative of e to the x is e to the x. Now I'll put my plus c. So the derivative of this entire quantity we're claiming is this quantity. I'm claiming. Well, actually, I can be certain. So if you go back to Calc 1, one question you should never ask is this the correct antiderivative? Because all you got to do is differentiate it to get back to the original. In remedial algebra, when you're learning how to factor polynomials and you've got a factorization, you don't say, is my factorization correct? You just multiply it back out again and see if you get the original problem. If you don't, then it's not correct. If I differentiate this and I do not get the original integrand, then this would be incorrect. So let's differentiate this. This is the only check you can possibly do. Right? So product rule, first times derivative of second, plus the second times the derivative of the first, then minus the derivative of e to the x, and then the derivative of c is 0. So let's see, I've got e to the x times 1 minus e to the x, and that leaves me with just x e to the x, which was our original integrand. Right, crowd goes wild, confetti everywhere. You did it correctly. So this is how you use integration by parts. It's essentially product rule in reverse. So the antiderivative of this was not one function. Calc 1 is you learned how to do all integrals where the antiderivative was just one simple function, right? Going one way or the other, like this one, like the antiderivative of e to the x. I know that one. But when I have a product of things, the antiderivative isn't going to be one function. It's usually going to be more complicated. That's where parts comes in. Right, so let's try another. Okay. So let's suppose this time we have, I have the integral of x cos x dx. All right. So if I have the integral of x cos x, actually, let me make that x squared cos x. Yeah, that's even better. I have x squared cos x. In the previous example, okay, you noticed that when I made u the x term, du is what shows up in the integral, and du was now simpler. It was the derivative of the x. So it turns out the majority of the time, not all times, but the majority of time when you have x to a power and you have a transcendental function like this guy, if you make the u be the x term, it's going to be simpler in the next step. That's usually which way you want to go. Now, again, remember, it's because I can integrate either one of these. So I will choose to let u equal x squared and dv to be cos x dx. Okay, when I do that, my du is 2x dx, and my v is the sine function. So after one step, I'm going to have uv. So this is going to be x squared times the sine function minus the integral of v du. So minus 2x sine x dx. I still can't integrate that one because I still have an x here. Oh, darn. I guess we did the wrong thing. Well, no, we did the right thing. Notice that was an x squared. That's just an x. This just means we have to do it again. Okay, we have to do it a second time. And if we make the same choice, then the x will probably be gone on the next step. So now I'm just looking at this problem right here. Okay, so I'll write it as a separate problem. For 2x sine x dx, I'm going to let my u be 2x and my dv be sine x dx. My du is then 2 dx. My v is then negative of the cosine function. So this integral right here will become uv minus the integral of v du. So it's minus, but that was already a minus. So this will be plus the integral of 2 times the cosine function. And you could certainly have factored that constant out. And so now this is negative 2x cos x plus 2 sine x. Now there's going to be a plus c, but I'm going to hold off because I still now have to do this. The value of this integral is this quantity right here. But notice it was minus the integral. So my final answer, I'll drop it down like this. I'm going to have x squared times the sine function minus this. So plus 2x times the cosine function minus 2 times the sine function plus c. Okay. So if I'm checking it through differentiation, if I do this well, I should get back the original integrand when all is said and done. Okay. So again, this is integration by parts, but because that x was raised to a power, it turned out I needed to do it 2 times. Very important that we recognize that. Now, having x doesn't always mean you're going to make this choice. Again, I said, if I can integrate both functions and one of them is an x, then I want that guy to be my u, because then the other guy is going to be less complicated as a result. So what if I have something like this? Oh, yikes. Does this mean I need to do it 4 times? Okay, well, if I make u be x to the 4th and then dv be log, then we have a problem. Here's the problem. If dv is log x dx, then what would v be? We know the derivative of the log. We don't know the antiderivative of the log. Oh, so I can't do this. Okay, I have no choice. My u has to be the log function because I don't know the antiderivative of log, but I do know the derivative of log. In the previous 2 examples, we knew the antiderivatives of both terms. That's why we actually could choose. In this case, I have to choose that as my u because I can only differentiate it. So in this case, we will let u equal the log function. dv is x to the 4th dx. du is then 1 over x dx. v is then 1/5 x to the 5th. Okay, so when I go through, we're going to get uv 1/5 x to the 5th log x minus the integral of v du. Oh, but wait a minute. 1 over x times x to the 5th, that's just x to the 4th. So this will be 1/5 x to the 4th dx. And I can integrate this. I am not going to have to do this in stages. I can do this one shot, piece of cake. So now I have 1/5 x to the 5th log x. This will be x to the 5th times a 5th. I already had a 5th, so that'd be 25th. Okay, so this is a perfectly good finished answer. Question is, not is it correct, it is correct. Is it the most useful answer? You see, if you're in a physics class, it is not unusual that you'll have to do repeated calculations. They're called iterations. And I like to use the example I remember when I was in physics. You had the little ramp and you had your little pine wood derby, like when you were in Cub Scouts, you know, and you're rolling it down the ramp, the little car, and maybe every 1/10 of a second, you're, you know, calculating the distance, and then you're trying to chart the speed and the increases, you know, stuff like this. You do stuff like this in physics, but I might have to do 30, 50, 100 separate calculations. If I've got a function where the variable shows up multiple times, that means there's a lot of button pushing. I don't care what kind of technology you have, you still got to enter the stuff. So in this case here, you know, there's a lot of x's, there's a lot of fractions. If I was going to have to evaluate this function repeatedly, forget about the c for a moment, just this part here, would it be more efficient perhaps to factor that answer? Now understand, you never have to factor an antiderivative. You factor derivatives because the first thing you always do with the derivative is you set it equal to 0. There is never a time while you will set an antiderivative equal to 0. So a factored form of an antiderivative is never required, but it's often prudent because it might make your life a little easier. You notice they both have an x to the 5th and they both have fractional coefficients. So if I factor out the smaller, then what I would have left is 5 log x minus 1. And if I had to evaluate repeatedly, you know, less button pushing now, less fractions, less x's. So this is the answer, but this might be a more useful form of the answer. If you're going to factor the fraction, factor the GCF, which is the smaller of the two in this case. To factor out a 1/5 and leave a 1/5 on the inside doesn't really make any sense. So this is the answer, perhaps a better form of the answer. But notice in the original problem again, I had x to a power, I had a transcendental term that couldn't be integrated. So I had no choice but to choose that one as my u. Okay, let's try another one. We got a couple more in us. And by the way, I did post, there's a set of notes with integration by parts on them, and there's also a video where I do some integration by parts. On the video, I'm doing a few more advanced versions of them because we're going to look at this a bit next day also. We're going to go a little bit more in depth. Some of the harder problems, in other words. So it might be a good idea to look those over before you start practicing problems, just to make sure you got it. So let's go back to, how about, all right, I want to do this. I just said a moment ago, well, we don't know the antiderivative of the log. Right, I don't know the antiderivative of log. So how am I supposed to do the antiderivative of log? Well, it turns out I checked this morning, the red phone rang, NASA was calling, the meteors are headed this way. They tried to contact Bruce Willis and the boys from Armageddon to go up there and, you know, blow it up, and they were busy. So it's up to us, and the plane's flying overhead immediately. Hold on a second. It's really loud at my end. It's up to us to figure out, we need the antiderivative of this so they can launch the rockets at the proper trajectories, and well, otherwise we might not be around tomorrow. Well, how are we supposed to do this if this doesn't have an antiderivative? Well, let's use integration by parts. Hold the phone. Don't I need two functions to do integration by parts? Well, you do have two functions. Does anybody see what the second function is? It's there. And just blurt it out if you see the second function.
Is it dx and ln?
No, dx is not a function. Dx is an instruction. It's not even part of
X and ln?
No, somebody
One.
else, right? Somebody
Is
said
it
it.
x?
No, that's log x. I can't-
1.
1. That's my second function. It says there, we just didn't write it. 1. How's that going to help me? Remember, that has to be my u. So that would have to be my dv. Turns out, this is kind of genius, to steal a term from Samuel L. Jackson. It's kind of genius right here. The fact that I'm taking a function that cannot be integrated, and I'm going to integrate it by using integration by parts, where a second function is simply the number 1. So if I let my u be log x and my dv be 1 dx, then my du is 1 over x dx, and my v is x. Now let's see if this works. uv minus the integral of v du. And you notice 1 over x times x is just 1. And it shows up again. But I'm pretty sure we can all handle this integral. This is going to be x log x minus x plus c. And I think we have just successfully integrated the natural log function. Let's do a quick check. And let's be absolutely certain. If I differentiate this, first times derivative of second plus second times derivative of first minus the derivative of x. Well, let's see. That's 1 minus 1 log x. Mini celebration. Turns out you have a lot of functions that you know the derivatives of, but you don't have an antiderivative formula, like the log. Think of your inverse trig functions. You can differentiate all of them rather simply. You can't integrate any of them. How do you integrate, inverse secant? How do you integrate inverse sine? How do you integrate inverse tangent? You differentiate them. But perhaps if we did this trick, I might be able to actually integrate them. It's kind of cool. All right, we're going to do one more example of this. This is probably the ickiest one of all. Just going to warn you. Well, yeah, maybe not the ickiest one. Maybe the ickiest ones we'll do Wednesday. We'll start icky. All right. I want to integrate e to the x times the cosine of x. Now, both of these are transcendental functions. Now, I've used that word already several times today, and everyone else, in a normal class situation, all the people in the front are going, oh, okay, sure, yeah. I have no idea what that means. I'm not going to ask, I'm too embarrassed. You actually have to, at this point of your math career, you absolutely have to know what transcendental means. You've been using it since remedial algebra and all through Calc 1, and you have a textbook that says probably early transcendentals on it. Every function that exists falls into one of two categories. It's either algebraic or it's transcendental. If it's polynomial in nature, it's algebraic. If it's trig, exponential, logarithmic, hyperbolic, inverse trig, those are transcendentals. When you evaluate polynomial type functions, you generally get rational numbers. When you evaluate transcendentals, you generally get irrational numbers. Okay, so if I took a polynomial, that's a rational, right? That's considered simple. If I took a quotient of polynomials, that's called a rational function. But if I took the sine of something, that's now transcendental. Transcendental functions are interesting, but they're harder to work with because you generally need a calculator to do most of the calculations. So I have two transcendental functions, but notice I can integrate both of them. Okay, I can integrate both of them. So therefore, my choice of u and dv, it actually will not make any difference in this case. I could go either way. So let's say you decided I'm going to pick, let u be e to the x and dv be the cosine function. Then my du is e to the x dx, and my v is the sine of x. Okay, so after one step, I'm going to get the integral of e to the x times the sine function minus the integral v du. So e to the x, right? So again, uv minus v du. Okay, so it's basically the same thing. Okay. Now the new problem I have looks a little different than the original, but it's the same type of problem. Okay, so now what we need to do is we need to integrate this one. So I'm going to do that one kind of off to the side. So let's do this one kind of off to the side. I'll write it right here. Well, let's see. what if we then, let's switch this time because, we got to do it again. And this time, let's make the u the sine function and the dv be e to the x dx. Then the du would be the cosine function and the v would be e to the x. So this quantity right here would be uv minus the integral of v, du. Great. Now I'll put this stuff back into here. So this is now, this integral here is now equal to e to the x sine x minus this. So minus this, so that'd be plus. Great. And now what do you notice? All right, we've got the integral of e to the x cosine of x is equal to the integral of e to the x cosine of x. Oops. We're back to the beginning, aren't we? My original integral is equal to my original integral. Yikes. I just somehow or another undid the entire first round. Does anybody have any idea what I did wrong? And by the way, there was something very wrong. I made an egregious error, and it wasn't in my choice up here. That choice was fine. Anybody want to try something?
You should have used the let u be ex again.
Yes.
E to the x. Okay.
This is an absolute, by the way. By the way, I purposely I'm taking wrong turns to show you things can go wrong. And just because something goes wrong doesn't mean you scrap the problem, right? The very first problem I did, I chose poorly. I went the wrong way, but then I showed you when you reverse it, it worked. This time I said, hey, let's switch our choices. The wise among you would say, why would we switch our choices? But I switched my choices. This is an absolute. Regardless of my choice here, if I switch the choice in round 2, you will always undo all the work. That's when it's necessary to do 2 rounds. You will always undo the work, which means this was a poor choice. But you have to see it. Otherwise, you may make that mistake yourself. So let's not choose poorly this time. Let's stick with the same choice. So once again, I'm going to let u equal e to the x, and my dv will be sine x dx. Now, I did tell you this one was kind of evil and kind of nasty and kind of gnarly, but let's face it, sometimes the evil ones are more fun anyway. So then my du is e to the x dx. My v is the negative of the cos x. So this quantity here will now be uv. So negative e to the x cos x minus the integral of v du, minus the integral of v du, but that was already a minus. So that will be plus e to the x cos x dx. Okay, so now when I substitute this in for this gives me e to the x sine x minus this, so that would be plus e to the x cos x minus this this is not a mistake. Before, what we got was this integral equaled itself, but this is the negative of the integral. These don't cancel. Everything we have now is absolutely correct. I'm going to erase this bottom row because I need the room, and we saw how that worked. You see, I don't actually have an answer to the integral. I have this integral equals a bunch of stuff minus the original integral. That feels like I'm going in circles, but I'm actually not. What if I said, let's add this integral to both sides. Remember, this is the left side, this is the right side. If I add the integral to both sides, on the left side, I'll now have 2 times the integral. And on the right side, I will have e to the x sine x plus e to the x cos x. And if you want to factor out the e to the x, that's fine. Remember, the problem was to find the value of this integral. I know what 2 times this integral is. Therefore, the integral that I was asking from the very beginning is simply 1/2 e to the x sine x plus 1/2 e to the x cos x plus c. So we have finished. What made this one particularly difficult was not the fact that we had to do it twice, but we never actually got to an integration we could do. We could do this forever. We're never going to undo. We're never going to get an integral that only has one term, because the e to the x and the trig term are never going to go away. But what we got was, we got the same term with different coefficients. That's why we could combine them and do this. That's a little tricky. It's not obvious, but it's the way it is. So like I said before, I've got extra lecture notes with practice problems. I've also got a video posted for this with practice problems. So we will take a break shortly, but not yet. I do want to make sure people understand, when you're doing a quiz, it is your work, nobody else's work. You can't get help from the tutoring lab. You can't work with another individual, and you certainly can't go to the internet. Okay, going to the internet actually is grounds for expulsion because it's plagiarism. And I had one student last semester who freely admitted, yeah, I went to the internet, I didn't know how to do it. They got a 0. On the first quiz, I have multiple people who got 0s and now are going to be turned into the deans for disciplinary action because they went to the internet to get their answers. How would I know that? Because on the first quiz, which only used day 1 integration techniques of polynomials, I had people doing multiple integrals, which, by the way, is an absolutely completely incorrect way of doing the problem. And since you don't learn multiple integration until late Calc 3, that means you had to go somewhere else to get it. And whatever internet site you went to, I hope you didn't pay money, because it was completely incorrect. You can't use a double integral when you have one independent variable. There is no math for that. It's a contradiction. But I had multiple people doing multiple integrations on the first quiz, even though we had a whole lecture on it, even though I posted a video on how to do it. So those individuals right now, I haven't gone through all the quizzes yet. So I have it indicated to those people. You will receive a 0. I'm going to turn you in. If it happens a second time this semester, you will be expelled from Mesa College. Your college career is absolutely in every conceivable way over. That is the worst form of cheating that exists, plagiarism. Plagiarism was when you take credit for work that is not yours. And since you didn't have any idea how to do multiple integration, you blindly wrote down something that should have looked strange at the very beginning. Now, are you kicked out of the class? No, I'm not going to do that. But that 0 will count, and that 0 may come in, affect you later. If that is what you have to resort to get through this class, then you should drop. You should have already dropped, because there is no possibility you're going to pass. And cheating right now is frowned upon. It's in the syllabus. It's clearly stated you can't use the internet. You guys all know this. Now, most of you did fine. Where I am a little concerned is the problems on the quiz I did in class. I also have lecture notes on the work. I did a video on centers of mass. Those problems actually should have been very simple. Not everybody found them simple. That means there wasn't enough practice. So you definitely want to do more practice, because this is far more complicated. So now I will stop recording.